Hello students. In the last video, we have discussed about the essentials of set theory. We discussed what is the definition of the set, and we discussed the set representation using the different methods like the roster method as well as the set builder notation. Right. So now in this video, we will be talking about the set operations. What are the operations that we can perform on sets? Right. So here is a summary for this lecture. So we will be talking about 4 basic operations, although we have 5 basic operations for sets, but we have already discussed one in the previous video. So the remaining 4 is union, intersection, complementation, difference, and the product. Product we already have discussed in terms of the Cartesian product in the previous video. So then we will be talking about some more insights on the set cardinalities, right? And we will see what are the set identities. We will prove those identities, and then we will see what do we mean by the membership tables, right? It's similar to the truth table. So let's start with first of all, what is Boolean algebra? So we are continuously discussing since the start of this course about the logic, right? So we discussed the propositional logic, we discussed the predicate logic. So propositional calculus and the set theory, right? They both, set theory and the propositional calculus, they both are instances of an algebraic system that is called the Boolean algebra. And this is really important. Whole computer science, electrical, engineering, they actually are built upon this Boolean algebra, right? So we'll discuss this in very detail in the coming chapters, mainly chapter 12, but we will be having different examples in different sections. Okay, so the operators in set theory are analogous to the corresponding operator in propositional logic. This we will see today, but most of the operators that we already have discussed in propositional calculus, that is or, and, the negation, right? So the similar analogies are used here in the set theory for those operators. So we'll see now. As always, there must be a universal set U. We discussed it earlier in the previous lecture. All sets are assumed to be subset of this set, universal set U, right? So what do we mean by union? You might have learned this union, intersection in your high school classes, but we need to understand it very clearly because most of the courses in because this course is foundation of computing, so most of the computing courses that you will be studying throughout your uh, computer science major, they will use the set theory and the logic, whatever we are studying in this course, right? So the definition of the union is, let A and B be sets. So we have two sets, A and B. The union of the set A and B denoted by A union B, right? So the symbol is used, A union B, capital sort of U is used for that. So what does it mean? It is all the element X such that X belongs to A or X belongs to B. So here you can see this is the logical OR that we discussed in the propositional calculus, right? So A union B means, so we need to choose all the X elements from A and B such that X belongs to A or X belongs to B. So it doesn't matter if it belongs to either from A or from B or either from both. So we choose all the elements and we make the set of that. So for example, if we have a set 1, 2, 3 and we have a set 3, 4, 5. So what's the union of 1, 2, 3 and um, uh, let me call this set A, let me call this set B. So what is the A union B then, right? So that's the set of element of A as well as the set element of B, since it is the OR operator. So that will be 1, 2, 3, 4, 5 and 6. So why 3 once only? Because in set we do not repeat. So 3 is member of both sets. We will write this one, right? So so you can see the solution 1, 2, 3, 4, 5, right? Okay, so there is no 6, sorry, no 6 in this set, in either of the set, right? So if we want to represent it using a Venn diagram, the union operation, here you can see this is set A, this is the boundary of set A, this is set B, and the union is this collection of the all the elements of A and B, right? All the elements in A and B. Intersection, the intersection of set A and B denoted by this symbol, right? This is the symbol of A intersection B, is basically the AND operation, whereas union is the OR operation, intersection is the AND operation. The technical definition is we need to choose all the X elements such that X belongs to A and X belongs to B. So we will choose only those elements will be part of the A intersection B that are present both in A and B, right? So note, if the intersection is empty, then set A and B are called disjoint sets. So if they do not have anything in common, right, so such sets are called disjoint sets, means they do not have, they are separate sets. So like for example, if we have a look over this Venn diagram, this is set A and this is set B that is overlapping. So set A have some elements, set B have some elements, and some elements are common. So this is the A intersection B, right? The common area, the elements that are common A and B. So let's see one example, 1, 2, 3, intersection 3, 4, 5. So what's the intersection of these two sets? That is obvious, that is only one element is common, that is 3. So element should be present both in A, both in B, right? So what is the intersection of this one? 1, 2, 3, intersection 4, 5, 6. So none of the element is common. So the result is empty set. So that means they both are disjoint sets. They are separate and different sets. They have different elements, right? Clear? Okay, so the complement. Now the third concept we are going to discuss is the third operation is the complement operation. Complement is similar to that we have seen in the logical, propositional calculus, propositional logic, that it's equivalent to the null operator, negation operator, not the null, sorry, negation operator. So if A is a set, then the complement of the A, right, with respect to some universal set U denoted by A bar. Sometimes we there are different ways to denote it. Sometimes we denote it using A bar, right? Sometimes we denote A complement like this one, and sometimes we write A C, right? So this is denoted by any of the term. So what is the definition? It is basically universal set minus A. So let me read it again. If A is a set, then the complement of the A denoted by A bar is the set U minus A, right? So let's write it mathematically. So A complement is basically set of X that belongs to the universal set such that X is not element of A, right? So if you look at this Venn diagram, so this is the universal set U shaded in the blue color, and this is white is set A, right? So what is A complement? A complement are all the elements in U that are not a member of this A. So outside this A, this is A, right? This is A. Outside this all is A complement, right? So this all is A complement. So so if U is the positive integers, so universal set is the positive integer less than 100, what is the complement of X such that X is greater than 70, right? So what's the solution? So our universal set is integers less than 100. I mean, starting from positive integers less than 100. So definitely what is the complement? So X is greater than 70 is the definition of this set. So the complement is definitely X is less than or equal to 70. So we choose all the elements that are not part of this set, right? Okay, so differentiation. Differentiation, we usually represent it with A minus B, right? So let A and B be sets. The difference of A and B denoted by A minus B is the set containing the elements of A that are not in B. So basically what happens, A minus B or the A difference B is all the elements that are present in A. Choose all the elements from A that are not present in B, right? So choose all the elements from A only those elements that are not present in B, right? So that's the definition of the differentiation. So is the set containing the elements of A that are not in B. So the difference of A and B is also called the complement of B with respect to A. So this is the definition. Let's understand it from the Venn diagram first. So this is the set A, this is the set B, and this is the common area, right? This is the common area, that is the intersection area. These elements are the A intersection B. But since these all elements are also part of the B, so we will exclude those elements, and rest of this A elements will be the A minus B. So we'll exclude all the B elements will be excluded, all the common elements will be excluded as well, since they are member of B, and only remaining element of A is basically the difference of A minus B. So we represented X such that X belongs to A, right? X belongs to A, it should be true, and X does not belong to B. So that's what I am saying. So we exclude all the elements that from the set B. So the definition is X belong to A and X does not belong to B. And sometime it is also called A intersection B complement, right? So you can see the B complement. What is the B complement? This is B. So B complement is all everything outside this B is the B complement, right? So if you take the intersection of A with this B complement, I mean intersection of A with U, so you will get only this A section, that is without this one, without the common elements. All right. So now let's see the cardinality once again. The cardinality of union of two sets. So before that, we know that the cardinality is this, the number of elements in a set, right? So what is the cardinality of A union B? So it is basically the cardinality of A plus the cardinality of B minus the cardinality of A intersection B. Why? Because cardinality of A will cover all this area, cardinality of B will cover all this area. So that means these elements are counted twice, right? That's why we need to minus these elements. So one time these elements will be minus, and that's why we are saying A intersection minus A intersection B. So the cardinality of A plus cardinality of B minus cardinality of A intersection B. So let's have one example. Let A be the math major in your class and B is the set of the CS majors, right? To count the number of students who are either math majors or CS majors, add the number of math major and the number of CS majors and subtract the number of joint CS math majors. Then only you will be able to get the exact number of students in this class, right? So we will return to this principle back in chapter number 6 and chapter number 8 as well, where we will drive a formula for the cardinality of union of n sets. So all these concepts are very much used. The whole set theory is also very much used in databases. The cardinality and all these concepts are also used in Boolean algebra as well as in relational algebra, that is the database language, right? So some review questions. So the set U is the set from 0 to 10, A is 1 to 5, B is 4 to 8. So what is A union B? So quickly you can tell me the A union B is 1, 2, 3, 4, 5, 6, 7, 8, isn't it? Right? So what is A intersection B? So A intersection B is just 4 and 5 because these two elements are common, right? What is A complement? So A complement is basically all these sets from the universal set except this A. So that will be 1, 6, 7, 8, 9, 10. Oh, sorry, 0, 6, 7, 8, 9, 10. Since 1 is there, 0, 1, 0, 6, 7, 8, 9, 10, right? So what is B complement? B complement would be 0, 1, 2, 3, then 9 and 10, isn't it? C, right? So A minus B. So A minus B is all the elements of A that are not present in B. So 4 and 5 are present in B. So rest remaining are 1, 2, 3. So A minus B is 1, 2, and 3. So how about B minus A? So B minus A is all the elements in B that are not present in A. So 4, 5, 6, 7, 8 are the element of B, but 4, 5 are present in A. So 6, 7, and 8 is the solution. All right. Now let's see what is the symmetric difference. Symmetric difference of A and B is denoted by this symbol plus with a circle, and we also call it in Boolean logic or the propositional logic, we call this operator, excuse me, uh, just wait 1 minute, let me just delete it. Okay, so this is called XOR operation, right? XOR operation that is very much used in Boolean logic and in computer science, building the computing chips, right? So what is this? This is the A minus B union B minus A. So what does this mean? So this is A, this is B. If you take A minus B, that is this set only, this portion, right? This portion only, right? If you take B minus A, that is this portion only. So what is the symmetric difference? Just exclude the common numbers. So take the A minus B and B minus A and union it. So exclude all the common numbers. That is called the symmetric difference operation. So for example, if you have a universal set from 0 to 10 and you have A, that is 1, 2, 3, 4, 5, B 4, 5, 6, 7, 8. So just uh, compute the elements of A symmetric difference B. So if we compute it, first of all we need to compute A minus B. So what is A minus? Let me just write it over here. A minus B is what we have computed in the previous slide as well. So all the elements of A that are not present here, that is 1, 2, and 3, right? And what is B minus A, right? B minus A is all the element of B that are not present in A. So that is 6, 7, and 8. So what is the A symmetric difference? B is 1, 2, 3, 6, 7, and 8, isn't it? So here you can see the solution for that. All right. So now let's look at the set identities. These are similar identities that we have seen in the propositional logic as well, right? And even in the predicate logic as well. So number one is the identity law. Identity law is if you take a union of set A with a empty set, you will always get the set A as a result. So that is quite obvious. A union empty is A. And if you take A intersection with union with universal set, so you will always get the A, right? So because A elements are the common element with the universal set, so you will get the A result. Domination law. Domination law says A union U means if you are taking the union with the universal set, you will always get a universal set as a result. And if you are taking A intersection with empty set, you will get all the empty set always. Why? Because there is no common element between A and an empty set. Idempotent law. Idempotent law is if you take a union of A with itself, you will always get A as a result, obviously. And similarly, if you take intersection of the same set, intersection of a set with itself, you will get the same set as a result. Complementation law, if you get the double complement, A bar bar, whole bar. So this bar and bar will be cancelled out, that remains only the A, right? Okay. Commutative law. A union B is equal to B union A. Yes, you can prove that. If you take A union B or either you take B union A, this is similar. And if you take A intersection B or if you take B intersection A, this is again, they are equal. So you get the same result. Associative law. A union B union C, all fine. If you take A B union C first and then take the union with A, no problem. If you take A union B first and then take the union with C, so you will get the same result. So that these two are equal. So order does not matter here, right? In this case, since you are taking both unions. And similarly with the intersection, if you are taking both intersection, A intersection B intersection C, no problem, you take the B intersection C first and then take the intersection with A. Or if you take B intersection A first or then take the intersection of the resultant with C, so this will give you the same result. That is called the associative law. Distributive law. Distributive law says if you take the A intersection with B union C, right? If you take the intersection of B union C with A, so what you can distribute is A. These are the similar laws that we have seen in the propositional logic. You can say A intersection B, and then you can take A intersection C and take the union of the resultants. So A intersection B, take A intersection of C and put the union in between. So you can always distribute this A intersection with B and with C, right? And since the middle operator remains same happens with A union B intersection C. So you can distribute this A union, right, with B, right, and then you can have the A union with C and put the intersection at the center. That's the distributive law. De Morgan's law, right? De Morgan law, we already know if you have A union B whole complement, so you can break this complement on A, you can break this complement on B, but reverse this operation. So if this is the union operation, this will become the intersection. If this is the intersection operation, this will become the union operation. And A intersection B whole complement means A complement union B complement, right? Absorption law. uh, you can absorption law is A union A intersection B is always A, right? So we have seen this again in the previous lectures as well with the propositional logic. So if A intersection A union B, this is again equal to A. So both are same. That's the absorption law. You can, by the way, prove it. Take some set, right? Given in the previous example, take these values. U is equal to from 0 to 10, and A is equal to 1 2 3 4 5, B is 4 5 6 7 8, and prove all these identities, set identities, right? From this slide to this slide and this slide as well. Complement law. Complement law is if you take the union of A with its complement, you get universal set as a result. That's quite obvious, right? So A complement is obviously the all the elements that are not present in A but or all are present in U, and this, when you take the union of these two, you will get the universal set. And if you take the intersection of A with its complement, you will always get an empty set, right? So you can prove it using the sets mentioned in the previous slides. How we can prove these set identities? Number one way that I have mentioned here, take some values, some sample sets, and then apply those functions and prove it. This is one way. But here we will discuss three different identities, three different methods to prove the identity. Number one is prove that each set, right, is a subset of the other. So this is one method. You can take one set and prove it by taking the subset of another. We'll see all these in detail. So that the second method is use a set builder notation and the propositional logic to prove it, right? And the third one is the membership table, right? So let's see how we can apply all these three methods on to prove the set identities. So proving a proof of the second De Morgan's law. What is that? A intersection B whole complement is equal to A complement union B complement. So let's prove it with the help of the first strategy, that is to take the subset. Each set is a subset of the other set, right? So we can prove it. We can prove this identity by showing that A intersection B, right, that is the left hand side, A intersection B whole complement is a subset of right hand side, that is A intersection union B intersection. And if we first of all we prove this, then we do this, and then we have to prove it on the other hand side as well. That means right hand side, let me just write it here, left hand side is the subset of right hand side, and then prove the right hand side is the subset of left hand side, right? So if you can do that, and you get the same values, if this is equal to this and this equals to this, then we can say they both are equal. Now let's do one example. So Okay, what are the steps in order to prove this, right? A intersection B whole complement is a subset of A complement union B complement. So when you know that X is an element that belongs to A intersection B whole complement, X is an element of that set, right? So if we resolve this complement, right? So take it out using the definition of the complement. That means if X belongs to A intersection B complement, so if we resolve this complement, then it means X does not belong to A intersection B. That we know, that's by definition of the complementation, right? Now by using the Boolean or the propositional calculus, and as well as the definition of the intersection, this is the intersection. If we convert this intersection into the definition of that, so that definition says X belong to A and this is intersection, and X belongs to B. So this X should be member of A, this X should be member of B, and but then this says not a member of, not a member of. So we apply the negation here, right, with the definition of this intersection, right? Now let's distribute this intersection inside by using the emergence law. So if I distribute this intersection here with this bracket, so negation X belong to A and negation X belongs to B, but then this AND operator will be converted into OR operator, right? That's obvious from the previous classes. Now if I distribute this negation inside, I mean apply this on this bracket, that is X belongs to A, that means X does not belong to A. Or if I apply this, X does not belong to B. So what's remaining? X does not belong to A or X does not belong to B. So if again we convert into the complement, that says X belongs to the A complement or X belongs to the B complement by definition of the complement, right? And if we convert back into it into the set or the by this is the if you see, this is what, this is the definition of the union. So that means if we convert it, so it says X belongs to A intersection A complement union B complement. That's the definition of the B. So we proved that by using some steps that this is the subset of this one, right? Now we have to do the second step, prove it otherwise. So we say that X is the element of A complement union B complement, right? Again, let's apply the union definition. What is the definition of the union? X belongs to the A complement of A or X belongs to the complement of B. That's here, right? Clear? Now let's apply this complementation. So X does not belong to A or X does not belong to B, right? So if we take this 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 not belong to in terms of the operator, so that means negation of X belongs to A or negation of X belongs to B. All right, then what happens? We say that this is, what is this? Let's take this negation common, right? Take it out as a common value. But if you take it out as a common value, like this will happen if you take it out, right? That is X belongs to A, right? Or X belongs to B, and this is the whole bracket, right? So what happens then? This is nothing but the definition of the union. Definition of the okay, right? So if we basically so yes, if you see this, this is the definition of the union, right? Sorry, definition of the, yeah, definition of the union. So if you convert it, that is X belongs to A and X belongs to B with the negation operator, right? So that's the definition of the intersection, right? Okay, so if you take it out, this operator will change with the AND operator, sorry. So this is basically the definition of the intersection. So if the negation operator is there, so that means this X does not belong to A intersection B. So if you take the does not belong, take it as a complement, so that means X belongs to A intersection B whole complement. So we proved in either ways, so that's why we call this identity is equal. They both are equal, so we can have this out of this and then we can have this out of this. All right, clear? So Now here you can see the second De Morgan's law again. I mean, using the set builder notation. First of what we have done so far, we have approved it using the assuming that the sub. I mean, that's each set is a subset of the other. We use this method. Now let's see how we can do it using the set builder notation. So right. So now let's see how we can prove the same second De Morgan's law with the help of the set builder notation. So A intersection B whole complement. So the definition of A intersection B whole complement is X such that X does not belong to A intersection B, right? So this does not belongs to means the negation operator. Negation of X belongs to A intersection B. So that means if we convert this into the definition of the intersection, that is negation of X belongs to A and X belongs to B, that's all right. And if we multiply this negation inside, I mean distributed, so that is X belongs to A, negation of X belongs to A, or negation of X belongs to B. All right. Then we say that if we apply this negation inside, so that means X does not belong to A or X does not belong to B. All right. So then we say X belongs to, if it does not belong to means A, means X belongs to the A complement or X belongs to the B complement. And if you see, this is nothing but the definition of the union. So that means X belongs to the A complement union B complement. At the end, you get A complement union B complement. So hence proved A intersection B whole complement is equal to A complement union B complement. So this is the set builder notation to prove the set identities, right? And then we have another method that is called the membership table. So membership table is similar to the truth table in the propositional logic. So for example, if you want to prove that A union B intersection C is equal to A union B intersection A union C. So you have three variables here, A, B, C. So put A, B, C over there and have the truth values for each of them. All the combinations, since these are three variables, so the possible combinations are 2 to the power of 3, that is 8. So 8 combinations you can see here. Then find the B intersection C, right? So you can see if 1 1 B intersection C means the AND operator, remember. So 1 1 is 1, 1 0 is 0, 0 1 is 0. So this is only true 1 when both are 1. Then you have to, so then you are taking this whole A union with B intersection C. So B intersection C you already have, A you already have, so take the union. 1 1 1 0 is 1, 1 0 is 1, 1 0 is 1, 0 1 is 1, 1 0 0 is 0. It's 0 only when both are 0, right? So then take this one A union B, right? So you can compute A union B. So 1 1 1 1 1 0 all, I mean this is true. This is 1 when anyone and either A or B is 1. We already know this this method. So take the A union C, I mean A with C. So again you got the A union C, and then take the intersection of this A union B and A union C. Take the intersection of this whole, that is this one. So if you take the intersection, you can see 1 1 1 1 1 1 is 1. So this is true for all this one. So here you can see these values and these values are similar. So we can say this left hand side is equivalent to the right hand side. So this method of proof is in set theory is called membership table, and similar method of proof in propositional logic is called truth table. All right. So let's generalize these unions and intersections. So let's say, for example, if you have multiple sets A1, A2, A3 up to AN, and they are, I mean, be an indexed collection of the sets, we define union of I starting from 1 to N, AI, and this I is indexed from 1 to N, AI union A1 union, A2 union, A3 union, A4 up to union AN. Similarly, we can write intersection of I from 1 to N. AI means I is starting from 1 and go up to N. So then A1 intersection A2 intersection A3 up to intersection of AN. So say for example N is 5, right? So this will go from 1 to 5. That means we have 5 sets, right? So these are well defined since union and intersection are associative. So for I is equal to 1 to infinitely, right? Let I, a of I be the I plus 1, I plus 2, I plus 3, and obviously these will be the indices. Then a union of I is equal to 1 to n. A of I starts with union of I mean the result is to n, I plus 1, I plus 2, so on. That is 1, 2, 3. And similarly, it goes for the intersection of the multiple sets, right? So that was the operations with the set. So that's all for this lecture. Let me just conclude what we have studied. We studied the set operations in this lecture, that is the union, intersection, differentiation, and the complement, and one more, that is the symmetric difference. Then we saw that the cardinality of multiple sets, like A, the cardinality of A union B, the cardinality of A intersection B. Then we discussed about the identity laws, and then we saw that how we can prove the identity laws. One way is the conventional way that we are studying from high school, that is assume few sets and then apply those sets to prove these identities. Then we saw three different methods here. One is the proving by taking the subset of each of each other, one method. The second method was using the set builder notation, and the third method was using the membership table. And at the end, we saw how we can generalize the union and intersection operator. So that's all for this lecture. See you in the next lecture with the functions, right? Until then, take care and bye bye.